an average of all your attempts to kind of encourage you guys to take the time to get the right answers as you're going through. I am anticipating making those questions available all together. So once all the quizzes are done at the end of the semester, I'm going to create a quiz that isn't graded, that has all questions in a bank so that you guys can use that to study over the break for the license exam. And then the written final will actually be a complete previous test that we have a copy of that you'll have to go through. And there are several of them. So you'll get one randomly when you sign into the quiz that is the final exam. But again, I'm going to make those open, and I'm going to try and get this Moodle left open for you guys until we do the NRC license exam. So you can keep taking those questions. And if you have a section that you're weak on, you can go back and keep getting access without it changing the grade you got in the class. So I'm trying to work that out so you have that all as a study aid, which I think will be super useful. Would you guys agree? Is that something that sounds good?
Yeah, they could probably even set up a separate Moodle page that you could just import that into.
Yeah, I'm not sure how they'll want to do it, if they'll just want to leave this one open or not. I'll work that out with them. But yeah, we'll have something so you can keep working on those practice exams. Okay, so let's talk about SAR Chapter 5. So a lot of what we talked about already with the safety analysis report is a whole lot of information that tells us about the reactor, about the instruments, about the physical location, and the geography and the weather that affects the reactor. But the safety analysis report would not actually be providing us an analysis on the safety levels of this reactor if it didn't look at accidents. When a safety analysis report analyzes specific accidents, they have a criteria that's called the maximum credible, right? And so what they're going to do is they're going to look at the typical types of accidents that affect reactors, and they're going to figure out which one is the most severe that is still likely to occur, right? So it's the maximum, but it's also credible, right? So we're not going to imagine that, instantaneously every safety system and every shielding system and every passive safety feature that we've put in the reactor just completely disappears, right? Because they won't instantaneously all do that. That's not credible. But we are going to look at the maximum of what can go wrong. All of the things that are active, for example, we'll say fail. And then we'll look at what temperatures and radiation releases we get, and that's our maximum credible. For the AGN reactor, the type of accident that creates the maximum consequences is a reactivity insertion, okay? For many other types of reactors, especially commercial reactors, there's multiple types of accidents that have to be analyzed, right? So there's going to be your maximum reactivity insertion, or RIA accident, reactivity insertion accident, so RIA. There's also going to be loss of coolant accidents, LOCAs, that have to be analyzed. We don't have a coolant pumping system, so we don't have to look at a LOCA, right? We don't have any active water going out of the core that we have to look at that. So that's not a credible accident, right? So while this is a great introduction to what accident analysis looks like in a SAR, just be aware in your careers when you go to a different type of reactor, there's really going to be a lot more involved in this part of the SAR. I think this is a great place to start and a great, training reactor where you get familiarity with this. But since you all have aspirations to be operators at larger facilities, just be aware. This is a very small picture of what accident analysis looks like. So, section describes the design features which ensure that the reactor can be operated under the specified conditions with no hazard to the health and safety of the operators, the other occupants of the building, or the general public. As we start to get into our accident analysis, there's going to be certain assumptions, right? So this occupancy, 100 to 200 people. There's an emergency plan that says that we will evacuate after a certain amount of time. There's going to be limits so that our systems can detect reactivity that's being inserted too quickly or temperatures that are rising too much. As we start specifying the assumptions that we have to have in order to ensure that this accident is actually controlled, this is where we're going to start connecting to our technical safety requirements, or the TSR, right? So out of the accident analysis in the SAR, we're going to connect to the requirements that we have to keep the system to that are specified in the TSR. So our SAR and TSR, even though they're separate documents, they are related and they create the safety envelope for which our reactor exists and operates in. So that's why we started talking about the SAR and the TSR in the same session we're talking about the end of the SAR. Does that make sense, what those two documents are giving you?
Yeah.
Okay. So, under normal operating conditions, the tank and concrete shielding are sufficient to protect personnel from undue exposure to radiation. So you can expect some sort of requirement in the TSR that the tank with its water and concrete shielding are actually there and have the right amount of water in them in order to operate the reactor, right? So it's saying, hey, this item, the tank and concrete shielding, provides this protection. Therefore, in our TSR, we have to protect that structure because it is essentially credited for providing safety, okay? Graham system and the administrative limit on excess reactivity ensure that a nuclear excursion does not occur. However, if this improbable accident does happen, then you're going to rely on the safety fuse to melt, essentially, and separate the core, which will prevent continuing reactivity insertion and avoid continuing maximum consequences or prevent the event from recurring, okay? In addition, there's shielding provided to protect anyone nearby from serious exposure and radioactive gas during this hypothesized accident, okay? So you should also expect in the TSR to see some requirements about the design of the core tank to hold radioactive gas. Okay. Back to some of this discussion on reactivity as we start talking more about reactor theory. In the text reading, I think that Tucker does a really good job introducing in simple and straightforward terms what reactivity is. And the quiz that's up in Moodle talks a little bit about some of those questions. But if you've done the reading in the first few chapters, I think chapters 3 through 5, he starts really talking about this. It's a really good introduction. We'll get a little bit more detail. The reactor physics portion of the NRC exam does require you to make some calculations with reactivity, and so we'll get into that. But essentially, what it's saying is that the total worth of all the rods here is this 4% delta K over K. And the insertion of up to 2% delta K over K, which would essentially be improper, should not damage the core as a result of the ensuing excursion, right? So when we talk about the allowable excess reactivity loading, what we're saying is we're trying to prevent any part of the core from being able to have enough reactivity to reach this 2% that we're talking about as our accident, okay? We don't have enough extra here. We have quite a bit more in all the rods together, but none of the rods get to move all at the same time, right? As we talk about some of our TSRs and interlocks, we are preventing the coarse control rod, fine control rod, and both safety rods from all moving at once so that we're never inserting this. So it wouldn't be the control rods that's giving us that problem. It would be an improper procedure or a fueled experiment in the glory hole, right? Still improbable, but that's where we could get this reactivity. When you guys read through this, did you have any questions about how the shielding and the reactor protects you, whether you're at the control station or in the building? Okay, I'm going to take that silence as you got it. So, our maximum licensed power level of 5 watts. What is the dose that we get while operating at that steady state level?
At 230 milligram an hour.
So this is in the concrete shielding, right? We don't actually ever get exposed to that. We get exposed here at the console to this 0.62 millirem per hour. Okay. This 230 millirem per hour, this is why there's a high radiation sign that prevents people from walking behind into that concrete area. Okay, right out concrete shielding, the shield surface gets 8 millirem. So inside the surface, 230. To the outside surface, 8. Right, so that's a huge reduction that our shield gives us. And then, of course, once we're actually at the console, it's less than 1 millirem per hour. Okay. What's interesting is that the entrance to the reactor laboratory has a slightly higher dose rate at max power. And if you think about how that facility looks, so Marcus and Sam, when you guys go in tomorrow, take a look at this. And then for Christy and Sue, the direction that the opening from the concrete shielding faces versus the complete wall that faces the console is why we have that slightly higher entrance dose rate. You know what I'm talking about, Christy and Sue?
I think so, yeah.
Okay.
Can you repeat what you were talking about just now?
Yeah. Because of the shape of the concrete, that little puzzle entrance, essentially, right where the high radiation rope is across, the opening actually points more towards the entrance. So you get slightly higher dose at the entrance to the reactor lab, whereas it overlaps and completely covers the console. So you have a slightly lower dose at the console. So when you guys get there tomorrow, Sam and Marcus, take a look at how that concrete shield wall is shaped, and you'll see why it protects the console more than people who are standing at the door. When you do the walkthrough portion of your exam, where essentially you're taking the NRC inspector physically through the facility and explaining to them everything you know about the facility, extremely important information. And this is stuff that I highly recommend that you have committed to memory. Know the dose rate from the neutrons and gammas from the surface of the tank. That's maximum steady state power is 230. And we restrict access to that area, so no personnel get that dose. Outside the concrete shielding, we're at 8 millirem per hour. And once we get to the console, it's at 0.62 millirem per hour. And because of the shape of our shielding wall, it's slightly higher at the entrance, but still extremely low at 0.7. So being able to explain that to the NRC inspector, be able to explain why there's a high radiation boundary across the entrance to that shielding area and why personnel are not allowed back there when the reactor is operating at high power will be extremely important concepts to convey on your walkthrough exam. Okay. Okay. Then it talks about some of the same information for the area above the reactor. The recommended limit for uncontrolled university areas is 0.1 rem per year to any student or member of the population. And so then it talks about if you have a 5-hour week, 30-week reactor operation, the dose that comes off at maximum power that leaves the reactor lab would be essentially that 0.1 rem per year at the entrance to the reactor room. Okay, so that's how we assure that we don't ever expose normal students who aren't operators and aren't monitored for radiation to radiation levels. Okay. New occupational dose limit, right? 1,000 millirem per year, right? So is this higher or lower than the DOE or NRC limits we've talked about in class before?
Lower.
Lower. Yes, much lower. Even though we have that 5 rem per year, that's the NRC requirement, we have a limited ISU of 1. Do you guys remember what that's called when you have a lower limit set by your company than the limit that's legally allowed?
Administrative control.
Did you say administrative control limit?
Oh, dose limit again.
Okay. Yeah, it's our ACL, our administrative control limit. You also need to have that memorized. You need to know what our ACL is at ISU. Okay. So one of the interesting things it talks about in the accident analysis is radiation damage to the fuel. We have low density plastic, right, that reacts differently than the metal you're typically going to see in most reactors. It can sustain radiation damage when exposed to neutron bombardment and radiation emissions from decay fissions. So Aerojet General Nucleonics puts 50 samples of the core into this test reactor at Argonne National Laboratory. So this is Chicago Pile 5. And they put it in a higher flux than we get at the AGN for a week. And essentially what happens when that plastic fuel is damaged by radiation, the density is reduced and there's hydrogen that's lost from that polyethylene matrix, okay? However, if we have the reactor at that maximum power of 5 watts for continuous operation for 200 years, we still aren't going to create enough radiation damage in our plastic fuel to matter, okay? So we could essentially put the reactor at its maximum power for the next 200 years, day in, day out, 24/7, and we would not be able to create the type of radiation damage that's going to start having that parasitic loss of hydrogen and reduction in density. And it's very important that our density in our polyethylene doesn't change because it's also our moderator, that hydrogen in the poly. So if we have a higher or lower density, we're starting to deal with an under or over moderated fuel system, which changes how it is controlled, because if it doesn't have enough moderation, you're going to have too many fast neutrons, right? That density is important. And essentially, we're at such low power, our radiation damage is just not a concern. I'll let you guys read on your own and review the production and handling of radioisotopes. There's also some procedures that talk about this handling process, okay? Main radioactive gases the AGN 201 produces. They're right here on the page.
Argon and nitrogen?
Yes, argon 41 and nitrogen 16. Essentially, because the core is surrounded by air and water, right? The glory holes, the access ports, it's in solution with the tank water, and then of course there is the tank full of water. you're going to have a lot of neutrons that interact with those materials, and they're going to produce argon-41 and nitrogen-16. We've talked in the materials class already about that production of nitrogen-16 from the oxygen-16 in the air. For the AGN, essentially argon-41 is produced, and then significant concentrations because of the low power we're at, okay? This argon is produced from argon-40, which just naturally occurs in our atmosphere, right? So if our air is from our atmosphere, it's going to have some argon-40. That becomes activated by neutrons, becomes argon-41. And essentially, these calculations are showing how much is produced, right? And then based on the dimensions of the room, how much will be in that space. And then we go to 10 CFR 20, and we have our derived air concentration, right? And so essentially, we have a regulatory requirement to have below a certain amount of argon-41 in the air that we might be breathing in the reactor lab, okay? And we are far, right? Operating at full power, we're at 0.0013% of the limit, okay? And we keep that even lower by having return air from the rest of the Lilly Bridge building. So we turn over the air and dilute it in the reactor lab. So you guys don't have to worry about inhaling argon-41 or nitrogen-16. Okay? I'm not going to go over the nitrogen-16 because we've talked about that in materials. But essentially their summary is it's insignificant because of our low power. So what the maximum credible reactivity accident is that we assume that add 2% delta K over K with the reactor at a power level below its maximum, even though we've controlled everything in the reactor, so the maximum extra reactivity we have in it is 0.25%. We're assuming that basically 4 times that amount is available somehow in our accident, right, to make it conservative. The situation clearly cannot arise during normal operation, but improper extraneous materials being inserted into the experimental facilities could potentially lead us to have 2% positive reactivity. This method of analysis, this is something that engineers have done in providing the design. And so what you simply have to understand as operators is that this is going to be prevented by controls on how the control rods have to be arranged, how much fuel loading they have, right? That's going to keep them below that 0.25% excess reactivity. And then controls on what can be put in the experimental facilities and how many experimental facilities can have material amount of time. Okay? Even with our maximum reactivity insertion, essentially what we would get from this 2% instantaneous release is a very high power level rise from our maximum licensed 5 watts to a maximum of 170 megawatts. However, once we get to that power, the temperatures that we're going to create are going to start activating our negative temperature coefficient of reactivity, and we're going to rapidly decrease the power level without operators doing anything. Just the physical design of the reactor is going to decrease that power back to about 800 kilowatts. We're also going to have melted our thermal fuse, and so then we're going to slowly decay. That rapid power rise, that melting, and then that rapid decrease will all happen within about 300 milliseconds. So even if as you, as the operator, make a big mistake and allow too much reactivity to be put into an item that's in an experimental facility, and you put that in and it's instantaneously inserted into the middle of the core. The core is going to protect itself in the case of that accident, and we'll get a maximum power, about 170 megawatts. The core fuse will melt, and then we'll return to a low power, and we won't be able to go high power again because essentially our core has split, right? So within a very, very short amount of time, that reactor is going to essentially use its inherent safe design in order to correct the accident that occurred. Okay? And this is going to talk a little bit about the time that's occurring and the power that you're going to see from that reactivity, right? So that's just the graphical representation about what we just talked about and what's in the reading. And essentially, this is going to talk about the doses that would occur at that accident. So understanding the maximum dose rate from that accident, okay? And then again, that maximum temperature that we're going to get is 128 degrees C, okay? So we're going to be able to melt that thermal fuse. Does that accident analysis make sense to you guys? Did you all do the reading before today? Are we reviewing stuff? Or is this kind of new and you're going to go read the details?
I read to about here. And then
Okay.
I skimmed the
What temperature does the, what's it called, the fuse melt again?
So if you go all the way back up to chapter 2 and the list of properties, it lists the melting point. That polystyrene, I don't remember it offhand, but I want to say it was about 100.
All right, thank you.
But
So
look at that table to refresh yourself.
When we were there yesterday, Jonathan pointed out that the water in the tank is almost where they couldn't run it. It's about 20 degrees Celsius. And he said that they can't run it if it gets over 25, I think is what he said.
Yes. So because of our negative temperature coefficient of reactivity, if the water tank is too warm because it's been warm outside, you can't start up physically. There's too much negative reactivity. And on very cold winter days, when the water is very cold, it adds enough positive reactivity that we can exceed our excess reactivity limit, and we also can't start up. Physically could in that case, but we are administratively not allowed to. When the water is warm, we physically can't start the reactor. Okay. And then it's going to talk about loss of water, right? So if the reactor is operated without water, the radiation level just outside the reactor tank will be 10 millirem per hour, 50 of fast neutrons, right? And these levels are 6 and 11 times as much as they would be with the water shield. So now it's going to talk about if that water shield leaked somehow, our maximum dose rate would essentially be an accident without that shielding, okay? So then it talks about the dose that would occur there. Then it's going to talk about the energy released, right? It's essentially just saying, hey, we produce this much energy, we make this much fission products, and then this is how much activity then from that fission product is contained in the core after these accident scenarios, which is important because we're going to need to re-enter the reactor at some point if we have an accident, right? And then it talks about the activation of the water and exposures inside the control room. So I'm not going to read all this to you guys. I just wanted you to get the important concepts from the accident analysis. All of this is discussing the dose that is associated with the accidents. Then here, it talks about designing our emergency procedures. We will look at the emergency procedures, but what's important to realize is that because we are producing such low amounts of energy and such low temperatures, honestly, it may not be obvious that our maximum credible accident has occurred. We could have this excursion and the core fuse, the thermal fuse could melt. And if we had a fault at the same time with our control console, the only way we would know that this occurs is our console telling us our power and temperature, right? So there's no external evidence. We're not going to see the tank change. We're not going to see water boil through a looking glass. We're going to see indicators on the control console of power and temperature, and our radiation monitors are going to go off. But if we're having some sort of accident, you know, that's maybe a natural disaster and those systems happen to be out, those are the only indicators we have. We won't have any other way of knowing that this accident has occurred. So other than our radiation instruments going up, we have to be able to evacuate the area if we have reason to believe that this excursion could have occurred, right? So we have to have controls on putting that material in the experimental facilities. And then we have to have a complete facility emergency plan, right? And this talks about some of the requirements for those. And we'll talk about that in more detail when we get to the emergency plan. Okay. Here are the safety devices that are credited, right, for preventing these accidents. Water level, right, so that we don't operate the reactor with a low water level. We also have our thermal safety fuse, right? Higher uranium density loading in the thermal fuse ensures that it produces more heat than the rest of the core, right? I believe that is a typo, and that's why that's highlighted in yellow. And then it talks about a earthquake switch, which will have an automatic scram, even though the structure itself is designed to be highly earthquake proof. And then it doesn't talk about, it talks about, you know, if there's a flood, there's no special precautions. Just deal with the flood. It's not going to get inside our tank or do anything. And we're not going to consider a storm. And then the negative temperature coefficient. So knowing that our safety features are the thermal fuse with its lower melting rate and its higher uranium density, our seismic scram, our water level, and our seismic trip. These are the things that we're then expecting to go find in our TSR as the things that would be controlled, okay? So now we're going to start switching to talking about the TSR. You guys see this? Yeah, okay, I can see it popped up. The TSR starts with giving some very specific, important definitions. I have never seen an NRC license exam that does not in some way ask you to understand the difference between a channel calibration, a channel check, and a channel test. So you need to know those definitions and you need to know them very well. Come on. Okay. There's definitions for experiments types. We're going to talk about excess reactivity more as we go through the reactor theory portion. You do need to know the definition for reactor shutdown and reactor secured. Okay. And then shall, should, and may. Shall, should, and may are things that pretty much throughout the industry, in our regulations, in our procedures, in our standards, they're going to be pretty universally using this definition. Shall is a requirement. When something says you shall do this, it means you have to do exactly this in this way. Should is essentially a requirement, but it's not quite as strong as shall, right? Should says that this is the correct answer, but there may be exceptions. It's not absolutely a requirement. In general, because of how conservative the nuclear industry is, there will be very few times where something says that you should do it or should have it, that you don't. It is essentially a requirement in that way. It's just worded such that there's a little bit more other options rather than shall, which is an absolute. May indicates permission. You can do this. You do not have to do this. So it's something that is permissive, but is not trying to be a requirement. Surveillance times in the TSRs, they're going to tell you that you have to measure and record some surveillance monthly, quarterly, yearly. Built into that is a definition of the grace period that you have. And so, for example, daily does not mean exactly every 24 hours. You have a certain amount of grace that you could do this in, and it still counts as within that daily surveillance time. This will be another thing as you read through that you should have memorized, because I have not seen an NRC exam that doesn't ask you if the surveillance for such and such system is daily and you complete it within 36 hours, are you compliant? And they're going to need you to know the surveillance time plus the grace time. Okay. Safety limits are, let's see, let's pull up the TSR here and let's look. So, they don't put them in here. So in this 10 CFR 50.36, it gives us a definition. A safety limit and limited safety system settings. Okay. Safety limits for nuclear reactors are limits upon important process variables that are found to be necessary to reasonably protect the integrity of certain physical barriers that guard against the uncontrolled release of reactivity. So the safety limit is the maximum that we're allowed to have for our process variables that are connected with protecting against uncontrolled release of radioactivity. So for us at the reactor, we're going to have in the TSR here, a safety limit on the maximum safe steady power level, right? The reactor power level shall not exceed 100 watts. Maximum core temperature shall not exceed 200 degrees C, either steady state or transient operation. Okay. Oh, look here. Here's our melt. Well, that's the polyethylene of the core. That's 200. That's not the thermal fuse. Sorry, Sam, that doesn't answer your question. But essentially, we have two safety limits, right? Reactor power level shall not exceed 100 watts. Maximum core temperature shall not exceed 200. Now, under that safety limit, we're going to have limiting safety system settings. Okay. These are the minimum functional levels that are put into our system for automatic protective devices, right? So if we have right here this safety limit that says 100 watts, 200 degrees C, we're going to have safety channels that initiate scram at the following limiting safety system settings, right? So we're going to scram at a setting of 6 watts, okay? And then the thermal fuse is essentially our protective system for the temperature, and it will melt at 120. Oh, there you go, Sam, there's your answer. The thermal fuse will melt at 120 degrees C. So we can't exceed 200 degrees C. That's our safety limit. Our limiting safety system setting is that the fuse will melt at 120. That's going to stop fission. That's going to stop the power from increasing. That's going to stop the production of thermal energy. That's going to reduce our temperature. We can't exceed this safety limit up here of 100 watts. And so we're going to have a scram that occurs automatically when our power detects 6 watts. And what's interesting is that limited safety system setting is already higher than our licensed power of 5 watts. So this is specifically talking about emergency situations, right? Our accident scenarios. We can't go above that 100 watts because we're going to generate so much fission that we'll be able to create a higher dose than we want. And so we're going to scram. We're going to keep going through these limiting conditions for operations, right? So they're going to talk about things that we limit on the operators, limits on experiments, how we get radiation monitoring and controls, and all of that is in the TSR. Administrative controls are going to be the things that aren't physical. So we'll keep going through that as we talk about the TSR, but you guys have to know that safety limit and those limiting safety system settings. That's another must have memorized, can't even think about it, have to know it thing for operating. Not to mention the NRC exam as well. Okay. I would suggest that you read this basis for both, because this explains the logic behind selecting that and why we do that to protect. And then we'll pick up next week and we'll keep talking about the TSR specification, the technical specifications, the limiting conditions for operations, and our administrative controls. Any questions? No? Does that all make sense? Do you guys see how our accident scenarios that we analyze and our doses that we're allowed to have feed into what we choose as our limiting safety system or our safety limit, and then how we choose limiting safety system settings to ensure we never get to the safety limit? Did that flow pretty logically for you guys?
Yeah.
I heard one yes. Is everyone else on the same page? Making sense? Okay, cool. We'll take those quizzes, and I'm really excited, Sam and Marcus, to hear what you guys think of your operational experience tomorrow. I think it's gonna be a lot of fun. Okay. See you guys virtually tomorrow.
There is a
Sue has
question.
the question.
I have a question, sorry.
Oh, yep.
So in the first assignment, that we have to submit those papers, like the medical papers and the radiation safety training.
I'm sorry, I can't quite hear you.
Just close down by the computer.
Is there anywhere?
Right there.
Right at the owl. Control.
Right there on the laptop.
Oh,
Yeah.
Okay. Can you hear me now?
Yes, I can.
Sorry, so in the first assignment, we were supposed to submit the medical paper and the radiation safety training certificate, and there was another thing that we have to specify what time we are doing our walk-in or not walk-in, the reactor time or something, the one we're doing with Jonathan. So how do I mention that? Like it just we have to submit the documents, but it looks like I have to write somewhere. And
Yes, so some people sent me an email and then they just put on Moodle that they sent me an email that had their medical form and their application and the copy of the screenshot from the certificate of the radiation training, and then the email they had with Jonathan where they scheduled their time. So I know you've joined in on Connor and Christy's time, noon on Wednesday. So you can just go into Moodle. Here, I'll show you if you want to look. So if you go to that, it should allow you to upload documents, right? So there's a option to upload documents or just write text in the actual submission. And so if you have a copy of the document that says, hey, I passed the radiation safety training, you can upload that, or you can send me an email and then just put the text in the assignment that says, hey, I sent you an email with all the documents and I am meeting with Jonathan Wednesdays at noon. Does that make sense?
Thank you.
Okay. And I think that I got all of that from everyone else already. I got several emails. I got the documents from everybody. So I think we're good to start moving forward. And everyone should hopefully get their dosimeters assigned to them soon. Thanks, guys.
Yeah, thank you.
Hey, Mackenzie,
Yes.
am I just giving those guys the two tan counters?
Yes.
They don't
That's
need
correct. No. No, so the radiation safety office is actually going to give us a survey meter to take with us. That's a better one than what we could have taken. So we're just going to get those two tan ones calibrated to take, and then they're going to give us one to borrow.
Okay. I'll head over there.
Thank you.